Welcome back. Functional Analysis FAV 023 Annexure by Professor Dr.A.G. Srinivasan. In this lecture, we shall prove one of the very classical lemma called Rees lemma. R-I-E-S-E-Z apostrophe S, Rees lemma. What the lemma says? It says if Y and Z are two subspaces of a normed space of any dimension. So the normed space could be finite dimensional or even infinite dimensional. Y and Z are subspaces of the normed space of any dimension. Suppose that Y is closed and it is a proper subset of Z. Then for every real number theta in the interval 0 to 1, there is a Z in Z such that norm Z equal to 1 and norm Z minus Y greater or equal to theta. This is going to happen for all Y greater or equal, for every Y belongs to Y. Now, how do you prove this? It's very easy. Let's prove now. Now, because Y is a subset of Z and Y not equal to Z, it means that there are some elements in Z which is not in Y, because Z is bigger and Y is a proper subset of Z. So choose element V such that V belongs to Z minus Y. Now what you do is, you take all such Y's in Y's and take the V minus Y and take the norm of that and the infimum of that. So what is infimum of this? Infimum of all V minus Y as Y belongs to Y, and this is called as A. The first point is A is positive. A is positive because of two reasons. One is infimum is the smallest element and all of them is going to be your norms. So norm is always positive. So smallest element also cannot be negative. So in that context, certainly A is positive. In the Rees lemma, it is said for every real number theta in 0 to 1. So I will take a theta in 0 to 1. Now, what is interesting is that when A is positive, when theta is a number lies between 0 and 1, then it is very obvious that 1 by theta is very large. Now, what we try to say is that when theta is very small, 1 by theta becomes very large. So in that context, A is greater than, A is less than A by theta. Because theta is a number lies between 0 and 1, as theta is increasing, 1 by theta is a multiple of, a larger number. So for any real number, positive real number A is less than A by theta. That's the first observation. And we already saw that A equals infimum of norm V minus Y. Therefore, A is less than or equal to, maybe equal to is not going to happen, but at the worst it can happen. V minus Y with the norm, of course, is less than or equal to A by theta, because A by theta is always bigger than A. That is what we are trying to write a step, that you can always find a Y naught in Y such that A less than or equal to norm V minus Y naught less than or equal to A by theta, where theta lies between 0 and 1 and A by theta is greater than A. Now define Z is equal to C times V minus Y naught, where C is 1 by V minus Y naught, norm of V minus Y naught. Now this norm V minus Y naught, let's define that C. What is C is? The C I'm just taking is 1 by norm V minus Y naught. Now this V minus Y naught cannot be 0, because if V minus Y naught is 0, this means that norm V minus Y naught will become 0. Okay, That's the first point. Second, if v minus y naught is 0, then v is equal to y naught. But y naught was chosen from y. V is chosen from z minus y. It is an element of z, but not in y. So this cannot happen. If this cannot happen, this cannot happen. If this cannot happen, this cannot happen. Therefore, C cannot be 0. Okay, this is not 0. So 1 by a real number is well defined. Not only that, this norm is always positive. We already saw it can't be 0. So this C is always positive. So C is equal to 1 by V minus Y naught. The norm of that is always positive. So if you take that C, where C is equal to 1 by V minus Y naught, then you can find the C is positive. Not only that, if Z equal to 1 by, if C is equal to 1 by norm V minus Y naught and Z equal to C by or C into V minus Y naught, the following observations are very obvious. Number one, what is norm Z? Norm Z is norm C times V minus Y naught, which is equal to modulus C times norm V minus Y naught. But C is positive, we already saw. So C is, therefore, modulus C is C itself. And therefore, C is 1 by V minus Y naught, which is not 0, into norm V minus Y naught. Therefore, this becomes 1. So what do you observe? If Z equal to norm, if C times V minus Y naught, we observe norm Z equal to 1. And C is positive, it means it's a real number. Therefore, this times V minus Y naught is certainly in Y. We will see that in the next step as before. So this norm Z is equal to 1. We would like to show that norm Z minus Y is greater or equal to theta as per the Rees lemma. The Rees lemma says norm Z minus Y greater or equal to theta. Now, what is norm Z minus? We'll calculate. Norm Z minus Y is norm. Z is C into V minus Y naught minus Y. C can be pulled out. C is a real number. Norm V minus Y naught. There is no C here, so I've taken C inverse. C is positive. Therefore, C inverse exists. So norm V minus Y naught minus C inverse into Y. Yeah. So norm C minus Y is equal to C times, because modulus C is positive, so modulus C is C times V minus Y1. What is Y1? Y1 is Y naught plus C inverse Y naught. Let me explain this once again to you in this step. So what is your Z? This is C times V minus Y naught. Now we will take C out. So what I get is V minus. So if just compare the step, we are taking C out. I take norm first and then do this. So what I'll do is I will take not this. I will take norm Z minus Y. This is norm Z minus. You know what is Y? What is Z is? Z is C into V minus Y naught minus Y. So I will take this term, which is equal to C times, because C is positive, so modulus C is C, norm V minus Y naught minus C inverse Y. This I will write C times norm V minus Y1, where Y1 is equal to Y naught plus C inverse Y. So Y1 is equal to Y naught plus C inverse Y. So what is V minus Y1? You will get this. What is interesting is that Y naught is from Y by definition. Y is certainly in Y. C inverse is a real number because C is positive. Therefore, scalar times Y is also in Y. Therefore, by addition, vector addition, Y naught plus C inverse Y belongs to Y. Therefore, Y1, which is equal to this, belongs to Y. That's an observation we make. So we observe that Y1 belongs to Y. And not only that, norm V minus Y1 belongs to A. What is the reason? Y1 belongs to Y, we proved just now. And what is the definition of the norm A? It is definition is infimum of all such y's, y belongs to y with v minus y. Now we have v minus y1. So therefore, this term will be at least A, or more than A, of course, is also possible. So norm v minus y1 is greater or equal to A. Therefore, norm z minus y equals c times norm v minus y1, which is greater or equal to c times A, because v minus y is greater or equal to A. But what is c? 1 by v minus y naught. And we already saw the norm v minus y naught is less than or equal to A by theta. So this is going to be less than or equal to, or greater or equal to, if you take the inverse, it's greater or equal to A by theta, because it's going to be greater or equal to, because it's the denominator. So A cancels, we get theta in numerator. So norm z minus y is greater or equal to theta. So we proved not only norm z equal to 1, we further proved that, z minus y is greater or equal to theta for all y belongs to y. So we proved the Ree's lemma. So kindly go through Ree's lemma. It's a very important lemma. Now, once you prove the Ree's lemma, we'll use that to prove the very important theorem on a vector space, a normed space. Now, before I prove this, recall what we have proved in this theorem. So, in the last video, we saw that if in a finite dimensional space, okay, M is compact if and only if M is both open and closed and bounded. In a finite dimensional space, M is both closed and bounded. So if M is compact, it is closed as well as bounded. If M is closed and bounded, M is compact. This can happen, this can guarantee only in a finite dimensional space. It may happen in n-dimensional space, but it is not guaranteed. But in finite dimensional space, it's very much guaranteed. Now, the next theorem says, very interesting theorem, we are going to use Ree's lemma to prove that, says that if a non-linear space, if X is a non-linear space, such that the closed ball set of all X in X, such that norm X less or equal to 1 is compact, then X must be finite dimensional. So what we saw in the previous theorem, if X is finite dimensional and if M is compact, it is both bounded and closed. Now we are telling if M is compact, what is M? It's a closed unit ball. Then certainly we are going to show in a normed space, it becomes finite dimensional. To prove this is very easy, we are going to use the Ree's lemma. What does the Ree's lemma says? It says that if you have a two subspace y and z, such that if y is closed and y is a proper subset of z, for every real number theta and 0 to 1, there is always an z in z such that norm z equal to 1 and norm z minus y greater or equal to theta. So I'm going to use this theorem or this lemma, Ree's lemma, to prove this. It's very easy to do it. Now we assume that M is compact. So we assume that this closed ball norm X less or equal to 1 is compact. What I need to show that is X is finite dimensional. We assume it is not finite dimensional. So assume that M is compact, but dimension X is not finite. If dimension X is finite, we have nothing to prove. So assume that dimension X is not finite. Now, the Ree's lemma is guaranteed for any dimensional space. That's an important point. The Ree's lemma is guaranteed for any dimension, even it is guaranteed for infinite dimension. So, because X is infinite dimension, we assume you choose a point x1 by Ree's lemma, whose norm is 1. Okay, whose norm is 1. Of course, some property it possesses, but I don't require that now. So, choose a point x1 with norm x1 is 1. For any dimensional X, there's always an Z such that norm Z is 1. So, choose an x1 with norm x1 is equal to 1. Now, this x1, this x1 certainly generates a one-dimensional space. I call x1. So x1 is being a one-dimensional space. You know that every finite space is closed. We already saw it some time back. So x1 is closed. Remember, every finite dimensional space of a normed space is always closed. So x1 is closed. Now, x1 is closed, okay? And dimension X is infinite. We assume that it is infinite. Sorry, this is not less than finite. It's equal to finite. It's actually infinite. Then, by Ree's lemma, you can always find an x2 in X such that x2 has a norm 1 and x2 minus x1 is greater than or equal to theta for some real number theta for every real number theta between 0 and 1, sorry. Now I'll check 0 equal to theta equal to half. So you can always find x2 such that norm x2 is equal to 1 and norm x2 minus 1 x1 is greater than or equal to theta. For every theta in 0 to 1, we will take theta is equal to 1 to 2, 1 by 2. Now this x1 and x2 generate a two-dimensional space again being finite dimensional. Again this x is closed. Again I'm using Reed's lemma. You can find x3 such that norm x3 is 1 such that norm x3 minus x is greater than or equal to half. Remember, norm x3 equal to 1, norm x2 is equal to 1, all that, all that, norm x2 is equal to 1, all that guarantees that this M is compact. I'm using that fact it is a compact set. Okay, that's because of that. So if you continue in this way, I can get x3 minus x greater than or equal to half. In particular, you take x3 minus x1 greater than or equal to half, x3 minus x2 greater than or equal to half, it goes like that. So you get xm minus xn greater than or equal to half for m not equal to n. That means this is a sequence xm such that norm xm minus xn greater than or equal to half. So what we try to say is that norm xm minus xn greater than or equal to half. It means that there exists a sequence xm first, but this xm cannot contain f subsequence. Cannot contain a convergent subsequence. Now, because of the fact it is always greater than or equal to half for every m comma n. And what is the xm as a property? That xm as a property is equal to 1. It means that this xm is also a member of m. And what is m? M is basically, all that xi's with norm x less than or equal to 1. So, but we assume that m is compact. Now we found a sequence where it is not having a convergent subsequence. This contradicts the fact that m is compact. We assume that m is compact. Therefore, the dimension must be only finite. So we proved that if this closed ball is compact, then the normed space must be finite dimensional. It's like, bringing finite dimensional space using the closed ball compactness, something like that. We have two more results to prove on this video. This is very interesting one and simple one to prove. It's very easy to prove also. If x and y are two metric spaces, if T is a continuous mapping from x to y, and if M is compact in x, T of M, the image of that is also compact. So what I try to say is that if x and y are normed spaces, let me write it here, x and y are normed spaces, T is a mapping from x to y which is continuous, M a subset of x which is compact. If T is continuous, the image Tm which is a part of y is also going to be compact. So Tm a part of y is also going to be compact. The inverse image of a compact, the image of a compact set under a continuous map is compact. Proof is immediate. It's only one line proof actually. So we'll prove it now. We wish to prove that every sequence yn in T of M contains a subsequence which converges in T of M. If you prove that, it's easy. Now, first of all, yn belongs to Tm. What is Tm? A subset of y. And what is y? Y is, the codomain from T to T of x comma y. It's a range actually in particular, right? Therefore, you can always find a Txn such that yn is equal to Txn, because yn belongs to Tm and y is a normed space. So you can always find a xn such that yn is equal to Txn. But xn belongs to m. But you are given m is compact. We are given, a subset of m is compact. We are already given m is compact. So xn belongs to m. Therefore, xn will contain a subsequence xn naught which converges to a point in m. Therefore, the corresponding image Txn naught, is also converges to the point yn, because xn naught is a subsequence, convergent subsequence, and because T is continuous, Txn naught is also convergent. We already proved a theorem that if xn converges to xn, if xn converges to x naught, then txn converges to tx naught if t is continuous. So since t is continuous, since xn naught converges, tx naught is converges to yn naught. So yn is a sequence which need not converge, but it contains a subsequence yn naught such that subsequence yn naught. This is yn naught here. It's not yn, it's yn naught. Let me just take a same blue color. This is yn naught. This is yn naught. This is yn naught, which converges using the property of continuous mapping. So this xn naught being a convergent subsequence and t is continuous, there is a subsequence yn naught. This yn naught actually, I think it's coming now. So it's going to be yn naught. I just write it here, yn naught, such that this yn naught, as a convergent subsequence. So we proved that T of M is also compact. Finally, we are going to show that under continuous map, see, there's an interesting part. Suppose you have a mapping T. The next result is if T is a mapping from X to Y and T is continuous, okay, then what you're going to show is that this Y will contain both the maximum point and the minimum point. So in a calculus class, if you take a function may not have maximum or a minimum, but now we are going to show if T is continuous, it's going to have the maximum minimum point. Of course, if M, a subset of X, is compact. So if the M is compact, then the Y will contain, the Y will contain the maximum minimum point. In particular, I'm going to show, of course, not for Y, it's for R. So for R, if T is a mapping from X to R, then this function will contain the maximum minimum point if X is compact. That's what we are going to show it. It's very easy to prove in just 2 lines. We'll prove it now. So a continuous mapping from a compact submetric space into R, okay, Y is R, always assumed to be a maximum or minimum point at some point of M. That's very easy. The first point is M is compact. You are given M is compact. M is compact. So by the previous theorem, we proved a T of M, first of all, is subset of R, because the mapping is from X to R only, not Y. It's R. And T of M is also compact by the previous discussion. And you know that, T of M is both bounded and closed. We already discussed in the previous class. Because if M is compact, then T is both bounded and closed. Therefore, if it is bounded, it should always have a maximum minimum point. That's what we proved in calculus class. Any bounded sequence will have a limit. Both bounded above means upper limit, bounded below means lower limit. But we don't distinguish bounded above or bounded below in our class. Only bounded is discussed. Because, when you take modulus, it is taken care of bounded above as well as bounded below. So this being bounded, you can see that it has inverse measures, and these will have the maximum point and minimum point. So we proved that if T is a continuous map from a metric space into R, which has got a compact subset, then R will contain both the maximum point and a minimum point. See you soon in FAV 024. Thank you. This is Professor Dr. A.G. Srinivasan. Thank you.